Vanakkam. Welcome to this course on biomedical instrumentation. So, we will introduce the course and run through some basics in this video. So, in this video, we will introduce ourselves to measurements, sensors and transducers. We will introduce ourselves to the concept of generalized measurement system. What are the characteristics, static characteristics, dynamic characteristics, and we will go through an overview of amplifiers, gain, bandwidth, impedance, frequency response, etc. And an overview of signal processing, filtering, high pass, low pass band, notch filters, etc. What are the sources of noise and reduction techniques? Critically, it is crucial to note the following disciplines come together in this broad field of biomedical instrumentation. What are the disciplines? First is physics. Physics, physiology. What is physiology? Physiology refers to functions of various systems. Functions of various systems in the human body. And because this is an instrumentation course, mostly we are discussing, when you say instrumentation, instrumentation refers to mechanical instrumentation, but here in this course we will restrict our attention to electronic instrumentation. So, this is essentially, we are working at the cusp of three fields: physics, physiology, electronics, and that is biomedical instrumentation. So, to do well in this course, to learn biomedical instrumentation, you need to focus on physics of the measurement system, physics of the instrument, the principle. What is the physical principle? That. And then physiology. What is the functional aspect or the quantitative parameter that you are interested in measuring? And then electronics. How is it that you are sensing? What is the measurement principle, electronic measurement principle that is there? All these three are almost equally important, although the focus is a little bit more on electronics aspect. The emphasis is more on the electronics and physics aspect, a little less on physiology, because this course assumes a little bit of knowledge of physiology, because if we start focusing on the physiology behind the measurement system, then that will become a course by itself, physiology for engineers, a separate course. There is no time for us to focus deeply on physiology. However, before entering into measurement of any system, before entering into a discussion of measurement of any physiological system, I promise to give you an overview, a relatively brief overview of that system. By no means that overview is exhaustive. To understand the physiology, to understand how that system works, you will have to go much deeper, but what this course will offer is a single class, usually one video of about 20 to 30 minutes, maximum 40 minutes of a given system. That is actually not enough for you to understand the physiology deeply. So, one prerequisite for this course, one can say, is that you need to know a little bit of physiology. Otherwise, you need to invest the time to learn that amount of physiology to do well in this course. So, the emphasis is a little bit more on electronics and physics and a little bit less on physiology. But we are still working at the cusp of these three fields: physics, physiology and electronics. This is biomedical instrumentation, and I welcome you, and I am super thrilled actually to welcome you to this journey of biomedical instrumentation. So, we introduce ourselves to measurements and sensors and transducers. So, what is it that we are interested? We are interested in measuring physical or physiological phenomena, physical and physiological phenomena. We are interested in measuring physiological phenomena. What are some of the properties of these physiological phenomena? These are inherently analog. These physiological phenomena are inherently analog and almost always continuous, and many of these physiological phenomena provide weak signals, not all of them, many of them, often weak, many, not all though, right. So, but the output may not always be electrical, but may be electrical also. Some of these outputs are electrical. You are wondering, is there an electrical output from the body? The answer is yes. For example, the best example is, of course, electrocardiogram is an electrical output from the body, or it can be mechanical. What is a simple example? Blood pressure, is it not? BP. It's a mechanical output, is it not? Or it can be chemical. What is a best example? Blood glucose level, is it not? So, ECG, what is the usual amplitude? In the order of millivolts. Blood pressure, typical healthy blood pressure is in the order of 80 to 120 millimeter mercury. Note the units. Glucose, what is the usual acceptable level? 70 to 140 milligram per deciliter, is it not? Temperature, it can be temperature. The usual values 36 to 37.5 degree Celsius. We know Fahrenheit values, but you can convert, there is a formula you can convert. Note that these physiological phenomena come in various dimensions and various units. There is a need to synthesize this information coming in from various dimensions to make sense of what is considered health and what is considered disease. Just one of them may or may not give an indication of health or disease for that matter. So, there is a need to synthesize. A lot of this work is still manual. That is what a doctor does, right? They synthesize information. What does the chemical blood work say? What is the blood pressure looking like? What is the temperature of the patient? What is the oxygen saturation level? All these things go into the decision making that the clinician, physician is making, so they can decide now what drug to administer. Should this be an injection or should this be a tablet? What should be the dosage, for example? All these things. So, that synthesis still continues to be largely manual, and it is not a formulaic principle. There is no simple formula, because if there was such a simple formula, then AI will do it. Then there will be no need for doctors. It is a lot more complicated than that, because it turns out that different patients are different. There is a need to tailor the therapy. It is a huge topic of research. How to provide patient specific therapy or patient specific treatment. Okay. So, coming back, what is the principle? What is our interest? Our interest is to get accurate physiological data. For example, these data. electrical data, mechanical data, chemical data, and for example temperature data and so on. So some examples of transducers are given, right? Pressure transducers. Some examples of digital pressure sensors are given. What is the difference between sensor and a transducer? We will discuss that. Right. The core principle is to convert physical quantities, in this case of physiological origin, physical quantities of physiological origin into numbers, quantifiable signals with units. Very important. It cannot be arbitrary unit, because in that case you cannot compare. Actually, there are some measurements that do lead to arbitrary units. In biomedical engineering, there are some what is the best example of this? What is the best example of measurements that actually lead to arbitrary units? What is the best example? Measurement of actually blood oxygenation levels usually leads to arbitrary units, because calibration of the blood oxygenation level, for example using IR systems, near infrared spectroscopy type of measurements, requires an extraordinarily challenging procedure. It is possible to calibrate it. There are devices that come calibrated, but the cheaper ones usually come in arbitrary units, which means that you can only use it to compare, but you cannot come to an absolute conclusion. So you need to understand what the limitations of such systems, right? Then we introduce the notion of transducers. What is a transducer? A transducer is a device that converts one form of energy to another form of energy. So that means it may convert, for example, a mechanical signal into an electrical signal, but the output need not be electrical, it can be something else also. So it is just an energy transformation system, or a device that converts energy from one domain to another domain, one form of energy to another form. Whereas a sensor is a sub type of transducer. Sensor is a type of transducer, in which case the output is almost always electrical. The input may be of any form, the output is electrical. Why is electrical so important? Because with an electrical measurement, I can digitize it and then process it using digital signal processing or a digital computer, or I can transmit it, for example, even across an ocean, and a different specialist living in a different continent can take a look. So electrical signals thus assume critical significance in this case. So a sensor converts, is a type of transducer that converts a signal of interest, a quantity, a parameter of a physiological parameter of interest into an electrical signal. The human body is indeed a challenging measurement environment, but why? Why is that? Why is that? Because low signal amplitudes, in many cases this is actually true, not in all cases, low signal amplitudes. Noise is generally high noise, which means what? High noise, low signal amplitude means immediately the basic electrical engineering knowledge immediately tells us that the SNR, or the signal to noise ratio, is not in all cases. In many of the cases, the signal to noise ratio is relatively low. Right? The dynamic nature, the dynamic range, yes, variable impedance in different cases, or impedance matching, etc., are challenging environments, and frequency response. These are all the various factors that come into the picture that make the measurement in the human system a little bit challenging. Right. For example, consider a digital stethoscope, not the regular stethoscope, a digital stethoscope. What this does is, we will actually in future weeks look at a digital stethoscope, in which if you use a film based digital stethoscope, what this does is it converts the vibrations on the chest wall into appropriate acoustic signals. So, it is a relatively complicated, relatively challenging transduction principle. Right. So, it is converting vibration that is felt on the chest wall into sounds. Of course, the general principle is to pick up the acoustic signals, but suppose you do not do that, you pick up the vibrations or movement of the chest walls, because in that case if you are interested in measuring the movements of the chest wall, then any noise that is coming from outside cannot actually affect it, thus increasing what is called as common mode rejection ratio. These things we will discuss in greater detail in future videos and future weeks. We have entire weeks dedicated to discussing these topics. A lot of time we will spend and invest on these topics. But if you use such a principle whereby you are only using the principle of movement of the chest wall to convert into hard sounds, then any sound, any ambient sound cannot cause noise in this system. Why? Because any ambient sound will not move that sensor. It is critical to keep thinking about this. Right. Also, one more thing is specificity and selectivity. What is the difference? What is the difference? Specificity is measurement of an intended measurement or measurand, intended measurand and nothing else. Specificity refers to measurement of an intended measurand and not something else. Right. How is this achieved? Using what are called as lock and key mechanisms. Need not be only chemical, but may be chemical. Lock and key mechanisms. That you have a lock that can be opened only by that key. Logically, for a lock, only a key or its duplicate should be able to open. If some other key is able to open that lock, then that is not even a lock. By definition, it is not a lock, right? So, so you need to have these lock and key mechanisms to ensure specificity. Or the other molecular recognitions, for example, at a deeper level molecular recognition. But in this course, we will not be focusing on molecular mechanisms, but that can be used. Just to mention that, that may be another method by which you can do that, right. Then you have selectivity. What is selectivity? This is the ability to measure in the presence of interference. There will be interference. Then you might say, oh, just reduce the interference. No, it is not that easy to reduce interference. There will be interference. Your ability to record in the presence of interference. For example, it is impossible to remove ambient noise, but I am interested in having high quality measurement, highly selective measurement. How to do that? That is called, that is high selectivity. That is the ability of a given sensor or a transducer to measure in the presence of interference, right. Critically, your measuring system should not interfere with the biological system. It should not affect the organism or the human. That is one. Your one measuring system should not affect measurement of a different measuring system. That is another form of interference. It should not affect the human or the organism. It should also not affect the other measurements that you are taking. Technically, that is a requirement. I mean, it is not always possible to follow this, but it is a critical consideration, right. So, it is useful to understand what are the properties of the sensor and the physiological system, so that you can appropriately choose the device for this. For example, I am interested in I am interested in continuous glucose monitoring. Well, okay. For example, this is a system in diabetes patients. I am interested in continuously monitoring glucose. right. Then you are interested only glucose. You are only interested in measuring glucose level, that is having high specificity. In the presence of variations of pH, variation of pH, variation of temperature and other interferences, right. There might be other interferences, pH might be varying, temperature might be varying, but I am still interested in measuring I am still interested in measuring glucose with high selectivity, right. By itself does not cause interference to other systems, does not cause, as in this measuring system should not cause interference. Now, when you are trying to measure with less interference, you should not cause interference, right, with other systems, to the biological organism or with other measuring systems. And should not have drift, that is should have what is called as baseline stability, very, very critical. These are some of the considerations while you are measuring this, right. So, with this we come to the end of this video. In this video we looked at introduction to measurements, what are sensors and transducers. Importantly, note that all transducers are not sensors, but all sensors are transducers. All crows are black, but all black things are not crows. Is it not? All crows are black, but all things that are black are not crows. Likewise, all transducers are not sensors, but all sensors are transducers. Fundamental difference, what is the difference? Transducers convert one form of energy into another form of energy, whereas sensors is a specific type of transducer that converts one form of energy almost always to electrical energy, something to keep in mind, right. Sometimes we think that higher sensitivity is always better. Remember, whenever you say always, that is likely wrong. Not true, because sometimes it might amplify noise also. Sometimes it might increase noise. Remember this. And people generally think that digital is always better than analog. But then when you say this, what do you mean by this? There is no such thing as a digital physiological signal. Sensing element is always analog, then you are converting to digital. So, this does not make much sense, because sensing elements are analog. So, this is not actually true or correct, this is a wrong notion, right. Many times students think that biomedical sensors are essentially just sensors that are used on humans. For example, biomedical pressure sensor is the same as any other pressure sensor, just that this is used on humans. This is not true, because there are some special requirements to be used on humans. Yeah. Also, sometimes students think that accuracy is the same as precision. These are two different things. Accuracy and precision are not the same. What is the difference? Accuracy refers how close you are to the true value. Precision refers to how repeatable your measurements are. These are two different things, okay, because usually students confuse the two. Accuracy and precision are not the same. Sometimes students also assume that non-invasive non-invasive measurements means 100% safe. This is not true. Some non-invasive measurements can also cause harm, some discomfort, some pain, some difficulty. That is possible. Just because something is non-invasive does not mean that it is absolutely safe. There are some non-safe, non-invasive measurements that are possible. Some things to keep in mind, right. So, these are all the things that we have taken a look at in this video. So, with this we come to the end of this video. Thank you for your attention.